Thank you all for joining us today for the webinar Accessing NHGIS Data in R. We're really excited to have you here. I will go ahead and introduce our presenter, Finn Roberts. Finn Roberts has been a senior data analyst at IPUMS since 2021, when he received his master's degree in biostatistics from the University of Minnesota School of Public Health. As part of the IPUMS spatial team, Finn uses his expertise in R package development to build tools that improve IPUMS data accessibility for the social science research community and support IPUMS data preparation and quality assurance pipelines. Finn has also developed workflows to integrate spatial data with IPUMS surveys for multiple interdisciplinary research projects studying the effects of climate change on population health. With that, I will turn things over to Finn. Thanks.
Thanks for that introduction, Kari, and thanks everyone for being here. Today, I'll be demonstrating some new tools we've developed in R to help you provide a new way to access NHGIS data. And before we get started, just a few logistics. Actually, I'll go ahead and stop my video here to improve the recording. We are recording this webinar, and we'll post it afterwards so you can access this. If you miss something, don't worry about that. You'll be able to get to the materials afterwards. If you have any technical questions about Zoom, send those to the host. Otherwise, if you have questions, use the Q&A tool that you should see in the Zoom toolbar. We have some people monitoring the question and answer forum, and they can provide some answers throughout the webinar. Or if we don't get to them during the webinar, then I'll take some questions at the end. So, all right, and without further ado, we can get started. So what are we going to cover today? Well, first, I'm going to give a quick overview of NHGIS. I assume that many of you are probably already familiar with NHGIS, but for those of you who aren't, I'll give a quick introduction. Then we'll talk a little bit about IPUMS R. This is our open source R package, which provides some of the tools that I'll be demonstrating today. And we'll do a little bit of setup with the IPUMS API to get you going. Next, I'll introduce a use case, a motivating example that we'll use sort of to guide our demonstration. And then we'll get into the meat of the webinar. I'll show you how you can query NHGIS metadata from R and how you can use those metadata to define, submit, and download an NHGIS extract. And then finally, I'll sort of show you how you can scale this up a little bit using the building blocks that I've introduced to build a slightly more sophisticated workflow that might be more approximate to a real use case. All right, so first, IPUMS NHGIS. NHGIS is the IPUMS product that provides summary statistics for the United States. So this is distinguished from other IPUMS products that provide microdata, which are individual records for households or individuals. NHGIS provides aggregate statistics, so counts, percentages, et cetera, that kind of thing for specific geographic units for the US. We have data from 1790 to the present at various geographic levels, going all the way down to the block level. And one thing that I do want to point out about NHGIS data is that there's 3 different types of data sources that we provide. The first is what I will call data sets and data tables together. This is sort of maybe what you would most commonly think of when you think of a census data product. Each data table represents sort of a single statistic or topic that is measured. And data sets contain a collection of data tables for a particular year and geographic level. Time series tables, on the other hand, are longitudinal data sources that have been standardized across time so that you can observe the changes in a standardized variable definition across a specific geographic footprint. And shapefiles are our geographic spatial boundary files, which you can use for spatial analysis or doing GIS work. And so the reason I mention this is because the distinction between these will be relevant to some of the stuff I show in a little bit. So how would you go about getting NHGIS traditionally? Some of you may be familiar with this interface. This is our web application where you can go and identify different data sources that we provide. You can filter through our options by time frame, by year, or by topic. And you can point and click and navigate the extract interface to identify the data that you'd like to extract from a system and then create an extract and download it. What I'm going to demonstrate today is a new way to do the same kind of workflow, except this time we'll be using our R package, IPUMS R. So one thing I do want to point out right off the bat is that the tools that I'm going to be demonstrating today were introduced in the version 0.6.0 release of IPUMS R. So this was released last summer. So you may have already had a chance to check out some of these tools. If not, make sure that you have the latest version of the package. Otherwise, you won't see some of the things that I demonstrate. If you've used IPUMS in the past, you can just reinstall it and you should get the updated version. And what this provides in this release is a new interface to access NHGIS data entirely within your R environment. So the web application that I just introduced, you don't need to do that. You can actually write code in R to do everything that you could do in the web app. So that includes browsing our metadata, defining an extract request, submitting it to our servers for processing, downloading the extract data when it's complete, and then loading the data into R. And I put a little star here because loading data into R, that was already available before this release. We did make some updates, so worth noting that some things might have changed a little bit if you've used some of our data loading functions in the past. But the point is that you can do this entire pipeline now within R. So if you're familiar with the web app already, you might be wondering why you should try to learn a new tool to do something that you already know how to do. There's a few main reasons I want to highlight. The first is reproducibility. So when you write your extract out in code, in this case, R code, it's much easier to regenerate an identical extract definition in the future. You just rerun the code and you know that you will get an identical extract definition. You don't need to go back and try to remember what selections you made in the web app or browse your previous extract history. As long as you saved that code, you can regenerate that extract definition. And this also makes it a lot easier to share your extract definitions with collaborators on a project or with reviewers who are trying to replicate your analysis, because you can provide them a consistent definition of exactly what data you used. The second is flexibility. So in many cases, it's as simple as just updating a single line of code to add an entirely new data source to your extract and therefore to your analysis. And also in R, we have comprehensive access to the NHGIS metadata. And so I know for myself, it's easier for me to filter through our metadata in R than it is in the web app. I just feel more comfortable with that. So that's just another advantage, is kind of more hands-on access to our metadata. And finally, you can automate your data retrieval workflows from our extract system directly and include them directly in your analysis. So for instance, you might query our metadata to identify when a new data set becomes available. And then if there's a new data set available, immediately add that to your pipeline and then to your analysis. So this is something that wouldn't be possible to do in this automated way if you had to go back to the extract system in your browser and point and click to access data. So some first time setup, just to get you started, if you haven't done this before, first you'll have to install our package. So you can do that by running install packages with IPUMS in there. Even if you already have package installed, again, like I mentioned, I would encourage you to update it if you haven't recently, to make sure that you have the latest version. And once you've installed it, you can just load the library into your session with library, and that will make all these functions available for use. The next thing you'll have to do for setup is to get an IPUMS API key. So much of the functionality that I demonstrate today is built on top of the IPUMS API. And if you're not familiar with APIs, don't worry. You don't need to be an expert on APIs to hopefully digest a lot of this content in today's demonstration. Basically, all an API is an interface that allows two different programs to talk to each other. So in this case, it will be our, the code we write in R can communicate with the IPUMS systems through the IPUMS API. But to use the API, you'll need a key. And the key is basically just a token that authenticates that you're a registered NHGIS user and you have permission to use the API. So to get a key, first you need to log into your NHGIS account. If you don't have an account, then you should register for NHGIS. I assume that most of you probably already have an NHGIS account. Once you have an account, you can go to this link that I've listed here, and that should send you to this page, which is the API key page. And what you'll see here is you'll see a long string here of digits. That's your key. And what I suggest you do is just click this copy to clipboard button, go back to your R session and put your key right in here and run this set IPUMS API key function. And so what this is going to do is it's going to save your key in your R environment for use across R sessions. So this is advantageous for a couple of reasons. First, you no longer will need to explicitly input your key every time you interact with the API, which would be very tedious. But second off, it also means that you don't need to actually write out your key in any of your code. If you're sharing your code or your code is publicly available, for instance, on GitHub or something like that, you generally don't want your key to be visible. Otherwise, someone else could use your key and make extracts on your behalf. So by saving your key in your environment, all the functions that I demonstrate in IPUMS they know to look in your environment for your key, and so they'll handle that on their own, and you don't need to worry about it. So if you run this line of code with your new API key, you should be good to go, and you don't really have to think too much about your API key after that. I'll also mention that everything I demonstrate for the rest of the webinar does assume that you have your key saved in your environment. Okay, so that's all the setup. Now we can actually get into using some of these tools I'm alluding to. So first I want to introduce an example that we can use to sort of guide the demonstration. I'm going to draw from this paper that was recently published by several folks here who are affiliated with the Minnesota Population Center. And in this paper, they generate several metrics to assess structural racism, and then they do an analysis of how that predicts birth outcomes in Minnesota. We're not going to do the full analysis, but what we will do is reproduce one of the metrics that they generated, and that is examining racial inequities in home ownership rates. So in the paper, they use the 2017 ACS 5-year data, and will operate at the county level for geography. The paper, I think, actually uses IPUMS, but we're just going to simplify that and go at the county level. And the method that they use is they first calculate the proportion of owner-occupied households relative to the total number of households for each of several race and ethnicity groups. So this gives us a proportion of households that are owner-occupied for each group. And then once they have those proportions, they calculated the ratio of the white non-Hispanic proportion to the proportion for the other race and ethnicity groups they were considering. So this gives us sort of a sense of how much disparity there is between the ownership rates for non-Hispanic whites and other racial groups in a given geographic area. So this is the example that we'll use. We'll imagine that we're trying to produce these metrics ourselves, and we'll go about obtaining data and doing so using IPUMS and the API. So just looking back again, I mentioned this at the beginning, but just to reiterate, remember there are 3 different types of data products that NHGIS provides. For this example, we're going to be focusing on data sets and data tables. We're not doing a time series analysis where we're looking at these metrics across time, and we're not doing a spatial analysis. So we're not going to be trying to obtain any time series tables or shapefiles. But the workflow that I demonstrate is easily generalizable to those data products. But just to sort of restrict our focus, we'll be focusing on data sets and data tables for this question. So in summary, really what we're trying to do at this point is we need to find relevant data tables that contain statistics that we can use to assess homeownership inequity. And so if you are new to NHGIS or new to this topic, you might not know exactly what data is available. And so to figure that out, you can start looking through our metadata. So NHGIS provides sort of loosely defined 2 types of metadata, summary metadata and detailed metadata. At least it's kind of the terminology that we use. Summary metadata I like to think of as just more a general listing of what's available. So a listing of all the available data sets, time series tables, and so on. To access summary metadata, you can run the get metadata NHGIS function. And so if we want to get metadata for all of the data sets that are available, we can provide the data sets keyword. And what that looks like when we get the output is it's a tabular formatted data structure with information about all the data sets that we provide. One column that I want to draw your attention to is this name column. All of the strings here in this name column are the names that you would use to refer to that data set or data source in general when you're defining an extract or interacting with the API. So for instance, if you wanted to obtain data from the 1790 census, you would use this 1790 _ CPOP keyword. You wouldn't type out, 1790 census like this. So most of them or all of the metadata really should have some sort of name information, and that's the name is always what you're going to want to use when you're creating an extract. So in our example, we know that we're working with the 2017 5-year ACS. So since this is a tabular data structure, we can pretty easily filter to identify particular data sets of interest. We'll use dplyr, which is commonly used for this kind of tabular data wrangling. If you're not familiar with dplyr, basically this filter function is just going to return all the records where this column group is equal to 2017 American Community Survey. So in this case, what we get is we have 5 different records that match that criterion. And so we have the 1-year ACS, which is not what we're using for our example. And then we actually have 4 different 5-year data sets. Most data tables are in the ACS 5A data set. So generally, if you aren't sure where to begin, that's the best place to start looking. And in fact, for our example, that's where we're going to want to look. So we'll home in on this data set, the 2013-2017 ACS 5A. And as I mentioned before, each data set is associated with multiple data tables. So this is where the detailed metadata comes in. Now that we've identified a particular data set, we can actually see the specific options available for that data set in the detailed metadata. We can use the exact same function to get this, though. So we still use get metadata NHGIS. The only difference is that now we can provide the specific data set name to the data set argument, and that should give us the metadata for that data set specifically. And so the output is a little bit more complicated here, but I've summarized it here. Some of it is similar to what you get in the tabular summary metadata, but we also have some more information about the available data tables, the available geog levels, and all of this is specific to this data set. So I do want to direct your attention to the data tables. As you can see here, this is an entry with 347 individual data tables. So there's a lot of tables in the ACS 5A. And what we can do is if we look at those data tables, we see we have another tabular structure that we can also filter through very similarly to what we did with the data set metadata. So in this case, we'll filter for a keyword. We'll use the string-r package, which gives us this str detect function, which allows us to search for a certain keyword. In this case, we'll look for tenure, and we'll look for it in the description of the data tables. And if we do that, we get all the tables that are related to tenure or home ownership. And there's actually 34 of them. And for consistency with the paper that I'm using as motivation, we'll pull out these 4 tables. So we'll look, the tables for each individual race group are actually split into separate tables. So we'll need each of these 4 table names for our extract definition. And so at this point, we have basically we have what we need to define sort of a minimal extract request. So we just need to take some of this information that we found in the metadata and put it into a format that we can then submit to the NHGIS system to process. And we can do that with the define extract NHGIS function. This is an aptly named function. This will create an extract request that we can submit to the NHGIS system. So what might a simple request look like? So the first thing that you'll do in a request is you can put a description in. This is up to you. You can put anything you want in here, and as long as it generally should be something that helps you remember what you've put in your extract. Of course, it'll make it easier to find if you ever have to go back to it. But the bulk of the request is made up of this datasets component. So here, hopefully some of this stuff looks familiar at this point. Here's the dataset name for the 2017 ACS 5A that we're using. And here are the 4 data table names that we identified in the metadata. And as I told you earlier, we're going to be working at the county level. You could have looked through the metadata to find out more information about the available geog levels. Just for the sake of keeping the webinar brief, I didn't do that here, but just know that there is more metadata available than just what I've showed. And the last little component here, you might be wondering what this ds_spec function is. And that's just whenever you make a data set and add it to your extract, you'll just wrap it in this little helper function. That just helps to bundle all the parameters that you want to request for that data set together. And this is mainly relevant if you happen to build an extract with multiple data sets. you'll need to kind of keep them each organized in their own specification sets. And I'll actually show an example of that near the end of the webinar. So if that sounds a little confusing, don't worry, you'll see it again. But once you've defined an extract, this is what it looks like. So you get a summary of the contents of the extract, and then you also see that it's an unsubmitted extract. So we haven't sent it off to be processed yet. To do that, all we have to do is run submit extract and provide the extract object that we just created to that function. And so you'll notice that I'm saving this back into a variable with the same name. This just ensures that we sort of keep track of the latest status of this extract object now that we've submitted it. And so if we look at that, what we'll notice is that everything's the same, except now we have a submitted extract and we have an extract number associated with that extract. So this number uniquely identifies the extract for a given IPUMS product and user. And so you can always use that number to go and find that extract. Now that we've submitted the extract, we need to download it, but it might take some time for the servers to process the request, especially if you've requested a lot of data. And so if you're running this in a workflow that requires that you make sure that the extract is ready before you download it, you can use this wait for extract function to ensure that the request is completed before you continue. So again, you just provide your submitted extract to this wait for extract function, and that will repeatedly check to see whether your extract is completed. And as soon as it is, it will return that extract back to you. So one thing to note is that running this function will tie up your R session until your extract is ready. That's not maybe always what you want to do. So just be aware of that. However, it is the best way to sort of confirm that your extract is ready before you continue. And then once it's complete, you can download it with download extract, and that should give you the path to the downloaded files, which I've stored here in our case in this NHGIS files variable. So yeah, if you haven't used NHGIS before, NHGIS distributes its files in zip archives. So you'll get a file that's named something like this. It's NHGIS with the extract number and then the file format. And those are all your files for your extract are bundled into one zip archive. Fortunately, we provide this function read NHGIS, which anticipates that your files are going to be in a zip archive. And so it reads them directly. You don't need to go and manually extract those files. This function knows that it's going to be dealing with a zip archive, and so it can kind of look inside and load the data through the compression. And what that gives you is, your standard tabular format data. As you can see, we have our county level data here, and this represents exactly the data that we requested, a few slides ago when we defined and submitted our extract. So at this point, now that we have our data, we can actually calculate our home ownership disparities. That was the whole point of this whole exercise. The one last sort of remaining problem is that the variable codes that you get in your extract might be somewhat esoteric. So it's not necessarily clear what AH39E001 refers to. So there's two options we have for getting a better sense of what these variables are. The first is that there is some limited metadata attached to the data when we load it. And so you can look at a particular variable, for instance, this AH39E001. We can use this helper function, IPUMS var info, that will give us a sense of the metadata for a particular variable in our data. So here we see that we're dealing with the estimate for the total, in this case, it's households, and for table AH39, which is tenure for Black or African American alone households. So this gives us a limited sense of it. One caveat is that some of these functions were designed primarily for microdata products, so they don't always scale to the NHGIS metadata structures as well. So it's possible that you'll get metadata in this way that's still a little bit ambiguous. That's why the sort of more robust option would be actually to go back to the same functions that I introduced at the beginning and use the metadata that we provide to look at the contents of a particular data table. So here we can run, again, the same function, get metadata in NHGIS, but if we specify a particular data set and data table, then we'll see all the information about the variables included for that data table. So in this case, the combination of the description, which tells us the race or ethnicity group in this case, as well as the variables table at the bottom, shows us exactly which variable codes map to which counts. So you can use this to inform your analysis code as you recode some of these variables or calculate other values from them. And so that's what we'll do next. So the first thing we're going to do in calculating these disparities is first calculate the proportion of homeowners in each race category. And so we can do that with the mutate function. Again, this is from dplyr. All we're doing is generating new variables based on columns that are already in our data. And so I didn't show all of this, but you'll just have to trust me that these variables are indeed the right ones. So this, for instance, is the owner-occupied households for white non-Hispanic population, and then this is the total households for the white non-Hispanic population in the denominator, and similarly for the other groups that we're using in this example. And then once we have those proportions, we can get the ratio of the white non-Hispanic proportion to the proportions of the other groups. And this gives us our homeownership ratios, which indeed was what we were striving for. And if we take a look at our data and select out some of these columns, we can see our ratios in our data at the county level. Also note, there are some infinite values here. I didn't really account fully for dividing by 0 or anything like that. So you might want to think about those kinds of things if you're doing this. But since this was just a simple example, I didn't cover that here. So at this point, we've calculated these metrics. I'm not going to go through the whole analysis that they do in the paper. But what I do want to highlight is that everything we've just done, you could put that into one single pipeline that fits in 24 lines of code in this case. So really, you can go all the way from requesting particular data to submitting, downloading, loading it, and then calculating new variables from the data all at once. It's pretty concise, and that's exciting. However, that might not really be the best workflow. If you look at this, if you change anything in this one long pipe, you are going to have to run the entire thing again, which means you're going to have to regenerate your data. So really, a slightly better workflow might be to split this into multiple files. You could have a file that generates your extract. So you could here we generate our extract, submit it, wait for it, and then download it to a specified directory. And then we could have a separate file that loads the data from that directory and does the metric calculation or the analysis. And this means that if we then change our analysis in some way, we don't necessarily have to regenerate and resubmit our extract. However, there's still some problems here. This is not particularly robust because if you change your data at all, then you're going to get an extract with a new number. And so your file name is going to change as well because the extract number is here in the file name. And so really a slightly better version would even be to, instead of hard coding this file path here, sort of write some code to dynamically check a particular directory where you're saving your data and maybe load the most recent file or something like that. But I'll leave that as an exercise for you. Okay, so that's actually the core building blocks of the workflow for submitting and downloading data. However, we can scale it up and make it a little bit more flexible. So a common use case might be, what if we want to make the same calculation that we just did, but we want to use multiple years of ACS data instead of just 2017? Certainly, we could build an extract by copying and pasting a lot of data set names and data table names, but that would be pretty tedious and also error prone. It'd be easy to make a mistake doing it that way. And finally, if we then wanted to continue to do that in the future when new data sets come out, we'd have to continue copying and pasting. And so it doesn't actually, make our lives that much easier going forward. But instead, what we could do is we could take advantage of the fact that ACS 5A data sets actually contain consistent data table codes across years. And this makes it pretty easy to iteratively build several data set specifications to include in an extract definition, which we can then submit all at once in a single extract. So how might we do that? Well, again, we start out by identifying the names of all the content we want to include in our extract. So in this case, we use the metadata function, get metadata NHGIS, to get the listing of data sets. In this case, we're filtering to get those records that contain the ACS5A string, since we know we're working with ACS5A. And if we extract all the names that match that code, we see we have data from, the 2005 to 2009, ACS5A all the way up to 2022. So, however, each of these data sets then needs its own specification in our extract. So this goes back to what I was mentioning before. We have this little helper function that defines the parameters for a given data set. Each one of those data sets that we just pulled out is going to need its own specification. And so the easiest way to do that is to iterate. And you could do this in a variety of ways. You might be familiar with writing for loops. You could easily do this with a for loop. I'm going to use the per package, which I think has a really nice, concise, and intuitive syntax for iteration. If you're not familiar with this package, we're going to use this map function from per. And basically what map is doing is it's taking each element in this vector that we provide. In this case, this is all the names of each of those data sets that we want to include in our extract. And it's going to do some function to each of them. And so in our case, the function that we want to do is create one of these data set specifications. And so we're going to create a specification for each data set. This X is just a placeholder for each of those data set names. And then because we can get the same data tables for each, because they of the way the ACS is coded with the same data table names, we can keep that hard coded and we can get them all at the county level as well. So what we're doing here is we're basically just iteratively building specifications for each of these data sets, without having to sort of copy and paste and doing it manually. And once we've done that, all we have to do is provide this list of data sets that we just created, this DS variable, to our extract definition. So if we just pass that right into the data sets argument, what you'll see is we now have our extract with, lots of data sets included. The output gets a little verbose with this many data sets, but at that point, you can proceed with the extract submission process just as you would for a simpler extract. Nothing about this part changes. The only thing that might change is that it might take a little bit longer for you to get your data when you're waiting for it. So this will take your new extract with all those data sets, submit it, wait for it, and then download it. One quirk that I do want to point out is that when you're requesting a more complicated extract, you might get multiple files in your extract. And when I say multiple files, I mean you can get a single zip archive that has multiple files contained within it. So what you can actually do is you can peek inside of a zipped extract with this IPUMS list files function. So if I do that in our case, we have one data set or one CSV file, I should say, for each of the data sets that we requested in our extract. So that's 14 in the data sets in this case. We can't load all of these at once by default. However, you can use this file select argument that we provide in read NHGIS to select an individual file from within your extract. So you can either do that using some helpers like this contains function that allows you to select the file that contains a certain string of text. So in this case, we would select the 2018 data, or you can provide an index just to match by position in the file. And you could do that. You could scale this up as well iteratively if you wanted to. You could iterate over each of these files and load them all if you wanted to. But I don't demonstrate that here, but that's perhaps an exercise for you to try. And so with that in mind, there are some other things that you might consider adding to scale this up even more. I've mentioned this already. It could be nice to automatically detect and add data for the latest ACS. That's actually sort of what we've already done. If you were to rerun some of the code that I just demonstrated, because we're using the metadata, as soon as a new ACS dataset is released, it will be present in your list of ACS datasets that you include in your extract. So we kind of already do this. However, you will, using the workflow that I just demonstrated, you would end up submitting, a large extract with every single ACS dataset every time. So you could consider maybe modifying this to instead just produce a new extract for the latest ACS and just add that to the data you already have for the previous ACS years. That's another option for sure. Another idea to make things a little bit more flexible is to dynamically recode variable names. As I mentioned earlier, the variable names can be kind of esoteric, and especially if you're iterating over many data sets, you might end up with a lot of different variable names. So one idea is to use the metadata where you can see the mapping between the variable codes and the descriptions of those variables to generate some more human readable variable names and automatically recode the column names with those variables. And this is something that actually some folks working with our data internally here at IPUMS have done for some of their projects. So this is certainly doable. It can be a little bit finicky because the variable naming schemes can be complicated or verbose at times. So you might need to adapt for your particular use case, but depending on what you're trying to do, that can be the helpful option. And one thing that can help with doing this is building your own sort of personalized functions to do some of these common processes that you might do frequently. So for instance, recoding these variable names, you might build a few functions that help you do that. If you want more ideas, I encourage you to check out our previous webinar on reproducible workflows. I'll include the link here so you can find that later. This focuses on using Python, but regardless of what programming language you're most comfortable with, there are some concepts in that webinar that really drill into a little bit more about how to write your code in a way that's a little bit more flexible and robust. So if you're curious about that, I encourage you to check that out. And finally, I just want to highlight a few other options that I haven't touched on in our example, but are important to point out. So obviously, you can request time series tables and shapefiles if you like. There's some slight differences. With time series tables, you'll use this TST spec helper function instead of the DS spec helper function. That's really just because there's slightly different options available for time series tables as opposed to data sets. So we need something slightly different, but it functions in largely the same way. And shapefiles don't have additional specifications available to them. So you can just request them by their name, which you can find in the metadata. The thing that I want to highlight about shapefiles is you don't read shapefiles with read NHGIS. Read NHGIS is really just for tabular data. If you want to load spatial data, I'll direct you to this alternate function, read IPUMS SF, which will load our shapefiles into SF format, which is provided by the SF package in R. And so previously, we did actually have an option to load tabular data and spatial data together and join them. We were worried that was a little bit error prone. Depending on the data in your extract, that could produce joins that were not valid. So now we encourage you to do that yourself. So you can load a shapefile with read IPUMS SF, load your tabular data with read NHGIS, and then join them yourself. And on top of this, there are a few other extract wide parameters available. So you could apply a geographic extent to the data you request. Note that this is only available for some data sets at certain geographic levels. Again, you can find that in the metadata, whether a data set supports geographic extent selection. You can also change the file format and things like that. So you can find more about these options in the documentation. And some last notes, the API and IPUMS do support several microdata projects as well. I've focused on NHGIS, of course, but we do also support USA, CPS, and international. So if you also work with some of those projects, you may be interested to explore that. In general, the workflow is largely the same. You still define, submit, and download your extract in the same way. The main difference is when you define an extract, there's different options available because of the different nature of those data products. So you'll have to look in the documentation for that, but you should be able to get started based on some of the stuff I've introduced today. And then you can also save and share extract definitions in JSON format. So this is nice if you want to sort of save a stable version of your extract definition in a separate file, which you can then load back into R if you need. And we have plenty more examples on the package website. So the link is here, and I'll include some more links at the end. And if you have any problems, you can always reach out on the IPUMS forum, or if you have a technical issue, or if you think you found a bug in the package or something like that, feel free to submit a GitHub issue on our GitHub repository. We're always open to working on stuff that you identify as problems or ideas for improvement. And here's a list of some of the links that I've alluded to throughout the project. This is mainly for if you come back to this presentation, you can find these links here. And with that, I'll say thanks for joining us.